I feel like when we talk about the atom, we spend a lot of time talking about the protons and the electrons. I mean, not without good reason. They are extremely important. The protons give an atom its identity. It tells us what element it is. It makes it really the substance that it is. And electrons, they determine the behavior of an atom. They give it its personality. They make it work the way that it does and react the way that it does and behave the way that it does. So ultimately, those two end up getting a lot of focus, but we always talk about neutrons and really never mention what they're all about. We often just say that neutrons are neutral and just kind of leave it at that. So, what is the purpose of a neutron in an atom? Well, remember that the neutrons are found in the nucleus, and the nucleus is this really dense, packed together space with the protons. And when you're thinking about what neutrons do, think of protons as being really lively, really outspoken, really intense people. And imagine squishing a whole bunch of them in one room. That's going to get a little unstable, right? And so what the neutrons do is they act as a buffer. They kind of like slide in between and let the protons actually kind of hang out together. And they really give stability to the atom. Here's the thing though, is you can do this with different amounts of neutrons, right? Like if you had this jam-packed room full of really intense people, you could kind of mix it up with a certain number of buffers and it would still be okay. It doesn't have to be like an exact number. And so that's what you end up seeing with the atom. Atoms can have different numbers of neutrons even if they're the same element. So let's take a look at some examples. Okay, so let's take a look at one specific element. We're going to take a look at the element carbon. And what I want to do is talk about the different ways that carbon can have neutrons and how that ultimately affects the atom. You see, carbon is going to have 6 protons because elements always have 6 protons. Or carbon always has 6 protons. Whatever the element is, its protons aren't going to change. But you can have carbon with 6 neutrons. So 6 protons, 6 neutrons. The atomic mass is going to be those two added together. So it is going to be 12 atomic mass units. And so this would be one version of carbon. But there is also another version of carbon. There is a version of carbon that, while it still has 6 protons, has 7 neutrons. You see, it has to have 6 protons because it's carbon, but 7 neutrons still allows the nucleus to be stable. It has an atomic mass of 13 atomic mass units, right? Just the protons added to the neutrons. But there's also carbon that has its 6 protons, like always, but 8 neutrons. And that gives it 14 atomic mass units as its atomic mass. You see, they're all carbon. They all have the same properties as carbon. They all undergo the same reactions as carbon. The only difference is some have a few more neutrons and ultimately a little bit more mass. This is what we would call an isotope. These are all isotopes of carbon. Isotopes are kind of like a version of an atom. So it tells us really about the mass and the number of neutrons, and because you can have different numbers of neutrons in an atom, you can have different isotopes of an atom. Think of isotopes like versions of a phone. You could have an iPhone or you could have your Samsung, but you might have a different version, right? You might have the like iPhone XS or the iPhone 6 or the iPhone 7 SE, right? There's a huge number of versions of them, but ultimately they're all iPhones. Same thing with Samsung. There's like how many versions of that, but ultimately all the same style. When it comes to atoms, you can have all carbon, but just slightly different versions as isotopes. Now, since The neutrons give the nucleus stability and allow that nucleus to actually remain clumped together the way that it is. And there are different versions of doing this. It means that some isotopes are more stable than others. To measure this stability, we use what's called the half-life. And what that means is we measure the amount of time it takes for half of a sample to break down and turn into something else. So let's say I add 100 grams of an unstable isotope. The half-life would be how long it takes until I have 50 grams, just half of that unstable isotope. This is a measurement that we use because it helps us measure the half-lives of these isotopes, and really it's based on the decay of them. As isotopes break down, they turn into different elements and different isotopes based on the type of radioactive decay that they go through. Now, to demonstrate this, I want to take a look at the example we looked at previously. So we looked at carbon. And so carbon as an isotope actually has about 15 isotopes. And I'm showing you the 3 that we looked at previously. And then I added one so we can take a look at a reference here. So carbon-12 is considered to be stable, meaning that it doesn't really have a radioactive decay because it's a really stable version of this atom. It's a configuration of protons and neutrons that allow it to actually exist without breaking apart. Same with carbon-13. 6 protons, 7 neutrons allows carbon-13 to be really stable and not break apart. But carbon-14, on the other hand, is not so stable. Carbon-14 breaks down roughly or half of it will break down every 5,730 years. See, that's the half-life of carbon-14. This half-life actually allows us to be able to measure the amounts of carbon. As living things take in carbon, they incorporate carbon isotopes of different varieties that exist in the air. So that means they have a predictable amount of carbon-14 in them by the time that they die. It's actually the same as the relative abundance of carbon-14 on Earth. And so over time, as they die, they stop taking in carbon, and that means that the carbon that is in their body will break down if it is carbon-14. We can use this idea to actually measure the dates of living things or materials made from previously living things because we can actually carbon date them using the half-life of carbon isotopes. But carbon has lots of isotopes, and one I wanted to demonstrate is the next highest mass, so carbon-15. Carbon-15 has a half-life of 2.449 seconds. It is so incredibly unstable that it will break down in just a couple of seconds. So that means that there's a really low amount of carbon-15 that exists because of its instability. You see, there's even carbon isotopes that exist for fractions of seconds, things that exist for like 30 nanoseconds in the case of carbon-21. And so there's lots of different versions of these isotopes, but really only a few end up being stable enough to be around for us to find. This is the idea behind isotopes. We talk so much about protons and electrons, but really it's the neutrons that allow everything to stay together. They give that buffer and that stability that allow for atoms to remain. And since there's so many different versions, it gives a lot of different variety into the ways that things can remain. So, thanks for watching, and I'll see you next time.